So let us start the new topic, that is single sideband. We also call it as SSB. Again, assume that we have a message signal to m of t. So this is our message signal. And naturally, this is a low frequency signal which we want to modulate. And it has a spectrum of this shape. So this is our m of f. So if we modulate it by using double sideband suppressed carrier, so in that case we would have this shape: upper sideband, lower sideband, upper sideband, lower sideband and upper sideband. But what if we can separate this into two blocks? Say we have a signal which is having a spectrum of m of f, and we call that this is our m plus of f. And then we have this thing that we may call as m minus of f. So in this way, we have segregated this spectrum into two parts. M of f would be equal to m minus of f plus m plus of f. So what we're basically trying to do is we are trying to construct a scheme for single sideband suppressed carrier. So if we take the inverse Fourier transform of this signal, so we would have m of t. The inverse transform of this would be m minus of t, and we would have m plus of t. So we have this inverse Fourier transform. So then we have m minus of t and m plus of t. So that is if we are considering just m plus of f, just one part of the spectrum. If this is all that you have, the inverse Fourier transform is naturally m plus of t. So what would be the characteristic of this time domain signal, right? So if we do not have a spectrum which is an even function, right? The magnitude which is not an even function. So this means that this m plus of t, basically this belongs to complex numbers. So this is a complex signal. So since this frequency domain magnitude plot is not even, so this means that this m plus of t belongs to complex numbers, right? So we can say that m plus of t, so this has a real part, which say we have a signal m of t that originally was real. So this signal is that signal 1 by 2 m of t plus as some complex part. So by complex we mean that this is having a complex number j by 2, and we say we have this thing which represents the complex part. This is a Hilbert transform of the message signal, or Hilbert function in time domain, right? So now this m plus of t belongs to complex number. It has a real part and then it has a complex part. So another property of this kind of function is that if you take the conjugate of it, that is if you take m plus of t conjugate, so this is going to give you m minus of t, and that m minus of t is over here. So m minus of t is 1 by 2 m of t minus j by 2 mh of t, right? So both of them are having real part and complex part. On the go, if you add this signal, that is m plus of t with m minus of t, right? So this term would cancel with this term, and this term would add with them. So eventually you would have m of t. So we would get back this expression again. So let us take this signal and then we use the Fourier transform. So we would have m plus of f, so 1 by 2 m of f plus j by 2 m h of f, right? So this is the Fourier transform of this expression. Let's say this is the first expression. So now this is our second expression. The same thing would happen if you take the Fourier transform of m minus of t. So at the same time, we have this function which is m plus of f. So that is, we had this function which is m of f. This was m of f, and we multiply it with something to eventually get m plus of f. So what is that something? So we would have a unit step function u of f that has this characteristic that for positive frequencies it has a value of 1, and for negative frequencies it has a value of 0. So eventually multiplying these two together would yield m plus of f. So we can say that m plus of f, so this is equivalent to m of f times u of f. This u of f, we can simplify it. How we can simplify it? So say we have a sine function of f. So this sine function suggests that whenever we have a frequency which is positive, the value is plus 1. And whenever it is negative, the value is minus 1. So say we translate signal, we say we have now 1 plus sine of f. So in this case, the negative value would go up. So we would have now up to 0, we have a value which is simply 0, and then we have a value which is 2. This is 1 plus sine of f. But if we multiply this with 1 by 2, so in that case we would have u of f. So basically what we're trying to do is we're trying to write u of f in terms of a sine function. This is for simplification. So this m plus of f, now this is m of f times u of f, which is now in terms of a sine function. That is, now we have 1 by 2 1 plus sine of f. So this is simply 1 by 2 m of f plus 1 by 2 m of f sine of f. So this is now our m plus of f. So let us say this is our third expression. So now we have two expressions of m plus of f. The first expression is this expression number 2, that m plus of f is equal to 1 by 2 of f plus j by 2 m h of f. And the second expression is m plus of f, which is equivalent to 1 by 2 m of f plus 1 by 2 m of f sine of f. So if we equate these two together, this 1 by 2 m of f would cancel because it is again appearing over here. So we would have this part link with this part, right? So that is, we would have j by 2 m h of f. So this would be equal to 1 by 2 m of f sine of f. Cancel this 2, and we can bring this j on this side. So we have, so this should be 1 over j, right? So we can say 1 over j times j by j. So this is equivalent to j over j square. So this is equivalent to minus j. So we can say we have a minus j sine of f m of f. So in that, basically this is our filter. So what we're trying to say is that if we have a signal which is m of t, if we pass it through this filter, which is h of f, right? So eventually we would have a Hilbert transformed version of this m of t. That is, we would have m h of t. So this is the thing that we added over here, right? So this is what we get. This is simply h of f, which is from this expression minus j sine of f. So if we are taking the magnitude response of this signal, that is we have h of f with respect to f. So in that case, we have for sine of f, if f is positive, so we would always have this outcome which would come for positive f. So this would be +1. For negative f, this would be -1. Right? At the same time, we have a j and a minus. But in the magnitude response, we are basically what we're doing is we are taking a square of the real part of h of f plus the complex part of h of f, and then we're squaring it. So this is our magnitude response. So regardless of whether you're having a positive one or a negative one, since we are squaring it, right, and then taking the square root, so we would always have a value which is +1 for all frequencies. So this is our magnitude response. But what about the phase response? A phase h of f. So this is simply tan inverse of this complex part divided by the real part. So if the frequency is positive or positive frequencies, so we would have tan inverse of -1 by real part is 0, right? So that is if f is greater than or equal to 0, and it would be tan inverse of 1 by 0 if f is less than 0. Why +1 over here is because of the sine function. So based on this intuition, we can say that the phase response for positive frequencies, this minus will come out. So we would have minus tan inverse of 1 by 0, and 1 by 0 is simply tan inverse of 1 by 0 is simply pi by 2. But then we would have this minus, so we would have a minus pi by 2 for all positive frequencies, and for all negative frequencies, this plus will come out, and tan inverse of 1 by 0 is again pi by 2. So for all negative frequencies, we would have the phase of plus pi by 2. So again, this is an odd function and this is an even function. So if I give a cos 2 pi fct to this filter, which is h of f. So let's take both the cases.
When f or omega is greater than 0, so as per the aforementioned plot, we would have cos of 2 pi fct minus pi by 2, and if the omega or f is negative, that is f is less than 0 or omega is less than 0, so in that case we would have cos 2 pi fct plus pi by 2.
Acha, no, let us come back to what we are actually trying to do. So we are trying to do a single sideband modulation. And by single sideband modulation, so this means that we have, this is a FC. So this is our FC plus bandwidth of the message signal, FC plus B, right? And similarly, we would have, this is our FC, and that is minus FC. So this is our minus FC minus B. The overall bandwidth is B or BM. But right now, what we are sending is we are just sending the upper sideband. So what is the expression of this one? So this is our M plus. So this is our M plus of F minus FC. Interestingly, what would be the expression of this one? Starting with M, would it be plus or minus?
Again, this was m plus of f, and this is m minus of f.
So this is M minus, not M plus, M minus. M minus of F plus FC. So basically what we are trying to say over here is that if you're just sending the upper sideband phi SSB of t, right? And because we're just sending the upper sideband, so we can say this is phi SSB plus of t. Or in frequency domain, we have this phi SSB plus of f, and that is equivalent to m minus of f plus fc plus m plus of f minus fc. If we are having the lower sideband only, what is this now and what is this? So this is moving from this point to this point. So this is basically minus f minus fc, and this is moving from here to here. So this is basically m plus f plus fc. So this was our fc. So this is fc minus b. This is minus fc. So this is my fc plus b. In this plot, what we are sending is basically we are sending the lower sideband, and that is now m plus of f plus fc plus m minus of f minus fc, right? So these are the two that we are basically sending. We can either not both of them one at a time. Well, we are just sending one sideband, not both sidebands. So let us again consider the simple one, that is the upper sideband only. So this is again our upper sideband. Now if I take the inverse Fourier transform of this, take the inverse Fourier transform, so we would have phi SSB plus of t from here, m minus of f plus fc, so we can say this is now m minus of t times frequency shifting property. So this gives us e raised to power minus j 2 pi fct m plus of t e to the power plus j 2 pi fct. So now we have m minus of t and m plus of t multiplied by two exponentials. The exponentials are coming from the frequency shifting property. But we have already defined what is m minus of t. So over here we have defined m plus of t and m minus of t, and they're nothing but 1 by 2 m of t plus j by 2 m h of t, and 1 by 2 m of t minus j by 2 m h of t. So what we have over here is simply 1 by 2 m of t. So this is minus, we have j by 2 m h of t e to the power minus j 2 pi fct plus again this is here, so we have 1 by 2 m of t plus j by 2 m h of t e to the power plus j 2 pi fct. To simplify further, we can extract out these terms, right? So this means that now we would have m of t times 1 by 2 e to the power plus j 2 pi fct plus e to the power minus j 2 pi fct. Then we can also combine these two terms. So we would have a plus m h of t j by 2 e to the power plus j 2 pi fct from here, and then from here with this minus sign we have a minus e to the power minus j 2 pi fct, right? So this is what we get. We can also say we can change this j to over here and this minus. Now from here this would yield simply a cos 2 pi fct. This is Euler's identity. So with this we have a message signal m of t, and from this minus, now this would again reappear over here mh of t, and all of this is basically again from the Euler's identity. This is sine 2 pi fct. And what is this? This is a time domain counterpart SSB plus of t, whereby we are sending the upper sideband only. So let us visualize this by means of a block diagram to understand it better. So say we have a message signal, that is we have m of t, and we take a thread, and then we have this cos function. So this is our local oscillator. We have cos 2 pi fct. So we use this local oscillator as a multiplier. So over here, all of this would be available over here, right, at this point. So next we need to construct this part, that is mh of t sine 2 pi fct. So we can again pull this thread and use a Hilbert transform h of f. If we use this transform, so this m of t would convert over here to m h of t. So we got m h of t. Next we need to multiply with sine function. So over here from the local oscillator we will use a phase shift of minus pi by 2, and we will multiply it with the output of this Hilbert transform. Eventually over here we would have m h of t times sine 2 pi fct, and then we are having a summation with this positive and this negative. So this is our ISSB plus of t, that is upper sideband modulated signal. So how did we achieve this construction? So this is basically based on all of this derivation that we have done previously. So let us start with the spectrum of the message signal. Say we have a spectrum which is having this shape, right? So this is 0, this is our m of f. Over here the spectrum is in terms of cos function. So cos function have two delta functions, which are these, one at plus fc, another one at minus fc. So this is basically over here. So this delta function is basically plus having a strength of 1 by 2 and 1 by 2. So over here at this thread we have, this is our 0. So at fc now we have again this signal, and at minus fc we have this spectrum again, fc plus b, and this is fc minus b, and same can be replicated over here. Try to visualize this part, that what would be the outcome of the Hilbert transform. So this is our 0, and we would have wave a spectrum of this shape. So what is this? This is simply m of f by j, and actually where is it coming from? So let us visit this again, that what is this filter doing, and that filter is over here. So whatever the input was, we are depending on the sine function, sine of f, we are multiplying by a minus j or 1 over j, that is over here, right? So for the positive frequencies we have an inversion of j. So basically for positive frequencies we have a flipped version. So this is basically flipped downward. For negative frequencies we get the same as is, right? So this is basically the spectrum that we get out of the Hilbert transform. So why is it so useful? Why this Hilbert transform is so useful? Let us again visualize by means of a spectrum again. So let us proceed with the next block. The next block is this sine function, and this sine function, it has a spectrum that is at fc. We have a delta function which is having a value of plus 1 by 2j, and at minus fc we have a value which is minus 1 by 2j. So this is our the transform of sine function. Now, if this is convolved with this sine function, all of this would be appearing over here, and again it would be appearing over here. So this means that this thread over here, we have, this is our FC, and this is again coming over here, but now inverted, right? That means we would have this spectrum. This is our M of F. This is the outcome, the spectrum that we receive after passing through the Hilbert filter, and that outcome convolved with the sine function yields this result.
Note that the complex number j will disappear since it's appearing in the sine spectrum as well as it is appearing in the Hilbert transformed version but in the denominator. So now we have these two spectrums and we have the summation with 1 plus and 1 minus.
The first one is this one, and the second one is this one, and they are being added over here, right? So this means that this is going to cancel with this because of this minus sign over here. This part, this is the lower sideband, is cancelled with the lower sideband of the set because of this minus sign. But at the same time, this upper sideband, this is added with a minus of minus this, right? So if you do this minus, so this will go up, right? And then it is going to add with this one. So we have got just the upper sideband with twice the strength of this and this. By twice, what do I mean? This was our M of F. Now over here we have 1 by 2 M of, this is F plus FC, and this is 1 by 2 M of F minus FC. So we have 1 by 2 over here, and again we have a 1 by 2 over here. So this will become 1. Similarly, now we have, if we subtract this part from here, so we would have this part which is 0. And if we subtract this part, but the negative of it from this part, so it will become something like that. So this is our upper sideband, and again upper sideband. So this is the eventual outcome. I'm just going to give you one glimpse that if you want to send the lower sideband, we can say lower sideband means this would convert to minus. That is the lower sideband, and this would convert to plus. Okay, so that means this minus is going to be added now. So this minus would change to plus from here. So in that case, we would be sending the lower sideband.
SSB looks promising. So do we have limitations for SSB?
Okay, so all of this is based on this filter, the Hilbert filter, and that is based on what? Unit step function, and that unit step function is kind of ideal scenario, right? So this means that, say we have a message signal which is having this shape, right? And in a way, what we're trying to do is we're trying to put a filter on this M of F, and that filter is say high pass filter. So after passing through that filter, now we have the SSB plus. Limitation is that you need this high pass filter, which is an ideal nature, and it has a very sharp transition. So that's not very practical. However, say we have a messy signal, right, and it shape something like this, and say up to 100 hertz, up to here, you don't have anything, and then you have a signal which is having a spectrum up to 4 kilohertz. Now, if we are going to modulate this in the SSB, so we are going to have this shape. And next, if we use the filter now,
which is non-ideal.
so in this case, we would almost have the upper sideband appearing over here, right? So in this case, SSB is very efficient. That is, we have a hole at DC. So SSB has some limitations when there are when there is a DC content in the signal.
Revisiting again the SSB modulator,
So this is basically suppressed carrier so far. So what are the changes that we need to do to make it with large carrier? How can we make it large carrier? So I need these carriers. This can simply be done by taking a thread, giving it a gain of, say, we give a gain of A, and then adding it over here. So in that case, we would have these two spikes that would appear in the single sideband. So this would become single sideband with large carrier. Basically A by 2 or A by 2. If we set A equal to 1, so this will become 1 by 2 and 1 by 2. If the DC content or this DC offset is not used, so we would need coherent demodulation.
which needs the exact copy of local oscillator at the receiver side and a low pass filter.
Right. So with the use of this A, we can use a simpler scheme, that is envelope detection. For the non-coherent demodulation, let us first say that what is this thing that we would actually transmit in time domain. So basically, we have phi SSB plus of t, and we had a messy signal m of t, and this was multiplied with cos omega ct, plus then we had mh of t sine 2 pi fct, mh of t sine 2 pi fct. So this is plus, so this would mean that this is basically minus. And with the DC offset, we are basically giving an A with the message signal A plus M of T, and we need to demodulate this, right? So if we need to demodulate this, we have to look into an envelope detection. And what is that envelope detection? So we have to find the envelope of this signal. We would take the square of this part, and then we'll take the square of this part, and then we would do the under root. So we would have A plus M of T whole square plus M H of T whole square. So that is basically envelope. The in phase and the quadrature phase. The coefficients of the in phase and the quadrature phase squared under root gives us the envelope E of T. We can bring out this A outward. So we would have an A, and then we would have 1 plus 1 by a m of t whole square plus 1 by a mh of t square 1 by 2. And then we can complete this square, so we would have 1 plus 2 by a m of t plus m square of t by a square plus 1 by a m h square of t, and again this is 1 by 2. Now we have few terms in which we have this a appearing, and then we have the message signal as well.
Note that in the last term we have 1 over a square.
So this is square. What is this a? This a is basically DC offset. So that is you're moving the signal upward by unit a. So this a and m, what would be the relationship between these two? Is a greater than m, that is the maximum value of m, or is it minimum less than the maximum value of m? Okay, if this was the signal m of t, at least we need to give this shift, right? At least. So we can say that the value of a must be much greater than this lower peak, or the maximum value if it is having the same maximum and minimum values. A has this has to be much greater than the peaks of message signal. So if this is the case, that is basically what is desired. So in that case, this A squared, actually this term would be approximately equal to 0 because A is much greater than message signal. And again, this term would also be approximately equal to 0. And again, based on the same logic, that A is much greater than m of t. So in the fourth equality, we have a 1 by 2 by a m of t 1 by 2. Now, based on this approximation, we can say this is now the fourth is not an equality but an approximation. Again, this a is much greater than m of t. So based on the Taylor series, we can bring this inward, and we would have a 1 plus m of t by a. If this is less than 1, so we can bring the power inward, right? So this is what we have done over here. And then we have a plus m of t. And then if we use, so in this way, the a would be removed, that is the DC offset is removed. So we would have m of t left, right? So this is basically non-coherent method of detection of AM, that is SSB.